analysis, we should be able to know why we perform structural analysis and what is linear static structural analysis. So why structural analysis is important? So structural analysis is important because it helps us to evaluate whether a specific product or whether a specific structural design will be withstanding the external as well as the internal stresses that are caused due to the forces or loads that are expected to be applied on that particular structure during its life cycle or during its lifetime. So what happens if we are going to perform structural analysis? We will be able to evaluate what are the different types of stresses that can occur inside the body or the structure on which certain amount or certain types of loads have been applied, and we can also find out or we can also determine the cause of the failure of the structure by performing structural analysis. Then after learning what is structural analysis, you should learn about two terms known as the linear and the static. So coming to the term linear, so what happens if we take a material, until the material crosses the yield point, what happens? There is a linear relationship or a straight line relationship that exists between stress and strain for a material. So what happens? Linear means straight. That means this sigma, which is nothing but stress, is equal to Young's modulus times of epsilon, which is nothing but the strain. And this particular straight line is given by the equation y equal to mx, which passes through this origin. So what happens in real life? After crossing the yield point, which is somewhere here, the material follows a non-linear curve. But when we take the assumption of linear inside the software, what happens? The software follows the same straight line. Instead of following this particular non-linear line, the software, even though after it passes the yield stress limits of the material, it is going to continue with the same line. So in real life, what happens? Component breaks into pieces after crossing the ultimate stress, but in software what happens? It doesn't show any breakage. So it just shows a single unbroken part with different colors or red color zone at the location of failure. So what you need to do as a CAE engineer, you should be concluding whether the component is safe or whether the component has breaked by comparing the maximum stress value with the yield stress value or the ultimate stress value, depending on what type of material you have taken. You may take ductile material, you may take brittle material. So depending on the type of material you have taken, you need to compare the stress values that occur in the component with the yield limit or the ultimate stress limit of the material, and conclude whether the component has failed or whether the component has passed. Then coming to the next term is nothing but static. So in order to define static, we should have two conditions. The first condition here is, see, the force should not vary with time. So dF by dt is equal to 0. Then the next condition is, at every node in the FE model, the equilibrium conditions, see, the force equilibrium conditions and the moment equilibrium conditions should be respected or should be followed. So why linear static structural analysis? So what happens is, 90% of the time the primary structural behavior of a product can be just understood by using the linear static analysis only. So in linear static analysis, what happens? There is a linear relationship between the applied forces as well as the displacements. In practice, this type of analysis is applied to the structural problems where the stresses are going to remain in the linear elastic range of the used material. Then coming to linear static analysis, the computation time as well as the computational cost, computational resources requirement are much less in comparison to performing a non-linear analysis for the same model. Therefore, what happens, in order to reduce the cost, reduce the time, reduce the amount of resources required, first an FEA engineer tries to estimate the behavior of a product using the linear static structural analysis. And once he is satisfied with the design, and then only he is going to go for the non-linear analysis or advanced dynamic analysis, and that too if it is necessary to understand the behavior of the product only. Then where can we find the applications of this linear static structural analysis? So we can find the applications for linear static structural analysis in different fields such as aerospace, automobile, marine, sports, construction, offshore structures, etc. So in whatever field we are going to apply FEA, the first and foremost starting point or the first and foremost basic analysis is nothing but the linear static structural analysis. In the next lecture, you are going to find or you are going to get more information regarding static structural analysis and how static structural analysis can be performed inside ANSYS Workbench. Thank you. Inside ANSYS Workbench, WB means Workbench. So how you can access static structural? So in order to access static structural, you need to go to the analysis systems first, and you need to expand the analysis systems, where you are going to get the static structural option here, and you can just drag it and place it on the project schematic like this, and you will see all the steps that are required to perform a static structural analysis. And here once you place this analysis system, the workflow is from top to bottom. So the first step we need to do is give the engineering material or the material with which the product is being prepared, and then we need to give the geometry of the object or the product, then we need to mesh it, and we need to give boundary conditions as well as loads, and then we need to solve this particular problem, and then we need to find out whatever results we want. So coming to the basics of static structural analysis, inside static structural analysis, the equation followed to solve a static structural problem is Kx equal to F, where K is the global stiffness matrix, and this is constant for a linear static analysis, and the assumptions are linear elastic material behavior is considered, as I have told you in the previous lecture, and the small deflection theory is used. Then coming to this F is nothing but the global load vector, and these loads are applied statically. That means no time varying forces or no time varying loads, and no damping effects are going to be considered. So this X is nothing but the displacement matrix. So what happens using this particular equations or matrices, the X will be solved. They can use many different types of solution methods. It may be direct solution methods, it may be iterative methods to solve these particular equations and find out the displacements at each node of the FEM model. Then coming to the geometry. So for performing linear static analysis, you can use all types of geometries such as 3D bodies as well as 2D bodies as well as the 1D body. Then coming to this surface body, if you take the surface body, what you need to do is you need to define the thickness from the details view under the geometry branch, and don't worry, we are going to see all of these things in the further example lectures. Then the cross section, if you take the 1D beam or say 1D geometry, the cross section and the orientation of the line bodies are to be defined inside design modeler and then are imported into mechanical automatically. In the design modeler session, we have seen how we can create a basic cycle frame using line models, and once we have created the line models, then we have applied different cross sections and orientation to that cross sections inside design modeler. So that is what we need to do for a 1D body, and then we need to bring that 1D body or 1D geometry into the ANSYS mechanical. Then inside mechanical, for every geometry you can have two types of behaviors. The first behavior is the rigid behavior, another one is the flexible behavior. By default, what happens, every body is assumed to be flexible. So if it is a rigid body, what happens, only loads and forces will be transferred, no deformations can be observed in that particular rigid body. But if it is a say flexible body, in addition to the loads and forces transfer, they can also have some deformations and other sorts of things. Then coming to contacts. So contacts is nothing but, say for example, if you take an assembly instead of a single component, what happens, two or more parts will be in contact with each other. So what happens, there will be a surface of this first part which will be in contact with the surface of the other part. So there we need to apply the surface elements or surface contact elements. you have a very good option inside ANSYS Mechanical, where when you try to import an assembly into Mechanical, it is going to automatically generate number of contacts for you, and most of the time these contacts are sufficient. But the only thing you need to do is you need to verify the contacts, and if possible or if required, you need to change the behavior of the contacts. Say for example, if we are going to create if the mechanical workbench has created its own contacts, the behavior of the contacts would be generally bonded, but if you want to change this particular behavior, you can change it manually. So we are going to see all of these things in the further lectures. And you see the mechanical contact pairs are usually color coded like this. If it is red, it is the contact side, and if it is blue, it is the target side. Then coming to material properties. So what are the material properties that are required for performing a linear static analysis? So depending on the type of loads you are going to apply, depending on the type of results you are going to request, you need to specify mechanical properties or material properties. So just for finding out the deformation, stresses and other sorts of things, you need to just specify the Young's modulus and Poisson's ratio of the material. So if you are going to add some inertial loads may be the loads due to earth gravities, acceleration load, rotational velocity. If you want to apply such a type of loads for any body inside static structural analysis, you need to specify density in addition to Young's modulus and Poisson's ratio, because if you are going to go for inertial loads, there the term known as the mass will come into existence in the equation, and that particular mass will be calculated from the density. And if you are going to add a temperature load to this, you need to give a thermal expansion coefficient for the material in addition to Young's modulus, Poisson's ratio as well as density. And if you want to find out this factor of safety and stress limits, you should be defining stress limits for this particular material which you have taken. And if you want to perform fatigue properties or fatigue analysis, then you need to give the fatigue properties of the material. Whatever the materials we have added in the engineering data, that will be available inside ANSYS Mechanical, and you can just change it from the details view. Going into mechanical and going to assignment, you can change the type of material you are going to apply for the component. Then coming to loads and boundary conditions, there are different types of loads such as a pressure load, line pressure, force bearing loads, hydrostatic pressure load, etc. Type of loads can be applied on the bodies or faces for the components. And you also have access to different types of inertial loads like standard earth gravity, acceleration, rotational velocity, that can be applied using mechanical in a linear static structural analysis. Then in addition to loads, in order to define boundary conditions, you have access to different support conditions like fixed support condition, frictionless support condition, cylindrical support conditions, displacement support conditions, etc. in order to simulate various types of boundary conditions. Then coming to the results. So once you have done everything, once you have given the loads and boundary conditions, defined materials, and then measure the material, and you solve the problem, you need to post process the problem. So what are the different results that you can see from linear static structural analysis inside ANSYS Mechanical? So what happens is you can find out the total as well as the directional displacements. You can find about von Mises stresses, normal stresses, shear stresses, maximum, minimum principal stresses, bending stresses, and everything that may occur inside the body due to the applied loads. Then you can also evaluate different types of strains. Then you can evaluate the factor of safety. You can find out reaction forces which occur at the boundary conditions, and we can also find out the contact status. In addition to all of these things, we have some view controls where you can use to view different sorts of results, and then we can animate all of these results to further analyze, to further understand the behavior of the structure. In the next lecture, we are going to see how we can perform a linear static structural analysis on a simple cantilever beam. Thank you.